Hi, Assalamualaikum everyone. Finally, we have reached the final chapter, chapter 6, filter design. For this video, I'm going to show you on the Butterworth filter design. Okay, we have two types of filter, which are Butterworth and also Chebyshev. So for the Chebyshev, we're going to continue in part 2. So basically, these are the contents for this video. A little bit on the passive filter circuit and also different types of filter response, and I'm going to show you the specification of filter, in particular Butterworth filter, and how we're going to design the function for Butterworth filter. So to recall back on the memory on filter, system designed to remove certain unwanted components of the input signal. So we have seen many of filter applications in the Fourier transform chapter, and when the unwanted components are described in terms of frequency content, the filters are said to be frequency selective. Okay, the term that when unwanted components are described in terms of frequency content. The main step to design a filter is first to produce the transfer function of filter in S domain, and the second one is to design the filter circuit. However, for the Butterworth filter, we are going to learn only on filter transfer function in S domain. There are two categories of filter design: analog for analog signal and also digital for digital signal. And for this chapter, or for this course, we are going to focus on analog filter, and there are two types of analog filter, passive and active. For this chapter also, we are going to focus on only passive filter. Okay, so these are some of the types of filter response that I can show you. So what is actually this diagram? This is actually a graph of magnitude versus frequency. And if you look at this rectangle here, this is actually a low pass filter, ideal. Okay, ideal low pass filter. So it has a very sharp edges here, and the roll off, it means that the rate that this line here drop. Okay, the roll off here is very sharp and very steep. And there are some other types, for example, Butterworth, Bessel, inverse, Chebyshev, elliptic, and Bessel. So all these types of filter response are different in terms of at the pass band here, in the response at the pass band, and also at the stop band. Okay, some have ripples, for example, Chebyshev and elliptic at the pass band, and some has very sharp roll off, for example, elliptic. Okay, and Chebyshev also can have a quite sharp roll off. However, for Bessel and also Butterworth, it has a very slow roll off. Okay, the rate that it goes from pass band to stop band is very slow. We are going to focus on the one that I have circled in red color here, which are Butterworth and also Chebyshev. Okay, this is an example of ideal filter response. So to recall your memory, we have pass band and we have stop band. Okay, we have omega c that differentiate between pass band and stop band. And for the normalized filter response, we have gain hj omega, which is equal to 1. When I say normalized, it is normalized at 1, and the stop band is 0. And there is no transition band. Transition band, it means the frequency range in between pass band and stop band. There is no transition band because sharp at omega c, the stop band begins, okay, for the ideal filter response. And in practical filter, on the other hand, the stop band gain here will not be equal to 0. Okay, for example, if you have a practical filter, it can be like this. Okay, so at the stop band, it will not stop at the gain here will not goes to 0. And no absolute stop band for the practical filter, okay, because there is no sharp edges here. So there will be a bigger transition band for the practical filter, so there is no absolute value for the stop band. Okay, we look at the Butterworth characteristic first. For this chapter, we're going to design the transfer function for the Butterworth. So Butterworth here have very flat amplitude response in the pass band. Okay, so at the pass band here, it has a flat, okay, no ripples. And for the roll off, it has steady rate of roll off. This is steady rate. Okay, it goes quite slow. And for filters of the same order, Butterworth filter has larger transition band than Chebyshev filter. So when I say transition band, is actually a range between pass band and also stop band. So within the same order, it means that Butterworth filter has a larger transition band, or the rate of the roll off is bigger. Okay, which is a quite when we say about filter, it is a unwanted characteristic. Okay, we don't want that. Because we want sharp roll off or very sharp edges here, so that it can resemble the ideal filter, okay, which is rectangular. So when the filter has a very slow roll off here, it is something that we do not want. Okay, so it has this the drawback here. And phase response is not linear as well. And however, there is no ripple here at the pass band. It is flat, and it is used when all frequencies in the pass band must have the same gain. Okay, because it has a very flat amplitude here. This filter is suitable for audio processing, and sometimes it is often referred to as a maximally flat response. So when you see in the question refers to maximally flat response filter, so you should know straight away that it is Butterworth filter. Okay, we're also going to learn another type of filter, which is Chebyshev filter. So the characteristic of Chebyshev, first, the obvious one is it has overshoot or ripples in the passband. So this is what we call ripples. Okay, it's like bumper here, and it is not flat. Okay, unlike Butterworth, where it has flat response, for this Chebyshev it has ripples. So the gain here means it's not the same. So however, it has better roll off than Butterworth filter. Okay, the transition between pass band and stop band is quite fast. Okay, because it has the sharper roll off, and roll off is the value of transitional frequency from pass band to stop band. However, like I said before, because of the ripples, phase response is not linear, and it is worse than Butterworth. And since ripple exists, it is not suitable for audio system. Because let's say, imagine that we have an audio system that goes through a signal audio that goes through this filter with different gain here. Sometimes it's loud, sometimes it's slow, and louder again, slow, loud again. Okay, so it is not really suitable. It is used, however, when we need a rapid roll off. Okay, so there is a trade-off between this Chebyshev and also Butterworth, in which Butterworth has a slower roll off, however flat response here. Okay, flat at the pass band, and Chebyshev has ripples at the pass band with better roll off. And amplitude of the ripple Amax here is proportional to the gradient of roll off filter. Okay, it has Amax here. Okay, so the amplitude of the ripple, it is proportional to the gradient of roll off. Means that if you want the sharper roll off, okay, the amplitude here will be bigger. Again, this is a trade-off, okay, of this Chebyshev characteristic. And if value of the Amax here is increased, the gradient of filter became better. Okay, so what do we want? Okay, do we want the gradient to become better, to resemble the sharp edges of low pass filter, ideal low pass filter, however, with the expense of higher value of Amax, means the ripples here becomes bigger. Right, and if we compare both Chebyshev and Butterworth filter response in one graph, okay, we'll see at the pass band here, Chebyshev, the black color here has ripple, and for the Butterworth it has flat pass band. For the roll off, Butterworth has very slow roll off, and Chebyshev has fast or sharper roll off. Okay, you also need to identify all these symbols. Okay, need to understand. This is a normalized filter. Okay, we have one maximum gain here, and versus frequency, we have alpha p here. So if you see alpha P here, it's actually a pass band gain or attenuation. Okay, so you some question use gain, some question can use attenuation. Okay, we represent it as alpha P, the gain of the pass band. So the gain of the pass band here, alpha P, will intersect this filter, and the intersection here at the frequency is called omega P, which is pass band frequency. Okay, so omega PC here refers to pass band frequency for the Chebyshev. Okay, and at the stop band here, we have alpha S. Alpha S here is stop band gain or attenuation. Okay, so this is pass band gain. This is stop band gain. Okay, so to remember, just remember S and also P. Okay, P here refers to pass band, S here refers to stop band. So alpha S refers to the stop band gain or attenuation. So the intersection with this filter Chebyshev, okay, will correspond to omega S, which is stop band frequency. Okay, so you see that the stop band frequency here, the gain of alpha S is not zero. Okay, because we do not have a very definite or ideal response in which at ideal response, okay, when we wanted to transition from pass band to stop band, okay, alpha will become zero. Okay, the gain of the pass band, the stop band is zero. Okay, so again, you need to remember alpha P corresponds to omega P and alpha S corresponds to omega S. This is for Chebyshev. And we have also cutoff frequency. Okay, cutoff frequency refers to 3 dB under 1, which is 0.707. Okay, so 0.07 here, if you draw the line here, it will correspond to omega C. Right, so for the Butterworth here, Butterworth, again, we have alpha P and we have omega P for Butterworth and alpha S and omega S for Butterworth. Now we move to how to design the Butterworth transfer function. A normalized transfer function of Butterworth for n order filter is given as, okay, H normalized, which refers to the transfer function, equal to 1 divided by B and S. So B and here is represented by 1 divided by S power of n. So n here depends on the order. So if second order of filter, so this is S squared, okay, plus A n minus 1, S n minus 1, blah, 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 until A1S plus 1. So Bn here is n order Butterworth polynomial, and the value of the coefficient an, a1, a2 up until an minus 1 here depends on n. Okay, the value of n, which is the order, and can be determined using the table F6a and F6b. And amplitude response for n order low pass Butterworth filter is given as this is actually h j omega like this. Okay, equal to 1 divided by square root of 1 plus omega divided by omega c is power of 2n. So it seems the equations here seems complicated. However, all are given, all formulas are given. Okay, and you can also refer to formula when you're doing your final exam later. Okay, it just that you need to understand the question. You need to know how to extract the information for question, and you need to know what equations that you need to use. Okay, basically this chapter is very easy. This part, okay, it's very easy. So there are more equations here. Okay, but you need to understand the function of each equation. For example, here the equation given here, the first one is the gain of pass band alpha p. Okay, so remember, alpha p here is gain or attenuation of pass band. Okay, can use both terms, whether gain or attenuation. So alpha p is given as this equation. Okay, again, you do not have to memorize. You can just refer to the list of formulas. And the gain of pass band alpha s at omega equal to omega s. Okay, because alpha here alpha S here corresponds to omega S is given as this formula. So the formula is almost the same except for alpha P, we use omega P here at the numerator, and for alpha S, we use omega S at numerator. Okay, so to find both equation here, to find both values of alpha P and alpha S, you need to know omega C, which is the cutoff frequency. Okay, so cutoff frequency here is given as the frequency when it intersects negative 3 dB down from the maximum gain here. Okay, so this is negative 3 dB, 0.707. If you log 10 0.707 and multiply by 20, you will get 3 dB. Okay, so for example, the Butterworth omega C is somewhere here. Okay, it's omega C, right? And then we can also use this formula, okay, to validate, okay, the alpha P and alpha S that we have. Okay, later on I will show you. And for the first, before you find the coefficients of the transfer function, you need to find the filter order. Okay, use this formula, which is also given in the list of formula. But the thing is, you need to properly insert the value here, whether alpha S and alpha P, and don't make a mistake. Because once you have the mistake of the number of order here, once you get a different number of order, then all your answers will be wrong. Okay, so this is divided by omega Sn. Okay, we will see the value of omega Sn after this in the list of formula. Omega Sn is actually normalized angular frequency. Okay, normalized angular frequency. And the cutoff frequency is given as either this value, this equation, or this equation. Okay, so how to use any of these equation, I will show you later. And this is taken from the list of formula. Okay, so you refer to list of formula that I have give to you. And it has here the gain, Hj omega, and also normalized transfer function. Okay, which is the final equation that you want to find. Okay, this is the final equation that you want to find. This is the one that we want. Okay, in order to find this, in order to find all these coefficient, you need to know the alpha P and also alpha S. Okay, so to calculate the alpha, you need to use the alpha P, you need to use this formula, alpha S, and for N is here, and this is for omega C. Okay, first we have example 1 to design a low pass Butterworth filter transfer function with the following criteria. So the criteria here is given. Okay, so this is a straight cut question where it is given. And normally for the final exam question, you need to extract that information. Pass band gain here is between 1 and alpha P, which is equal to 0.94. Okay, so 0.94, if you put in the punch in the calculator, okay, you punch in the calculator, so you put log 10 of 0.794, and then you multiply by 20, you will get negative 2 dB. Okay, so this is given straight to you, so you can use this 2 dB. You need to use in dB. Okay, you need to use in dB, and this is given from omega 0 to 10. So it means here omega P is equal to 10. And stop band gain here not exceed alpha S, which is equal to 0.1. You need to change it in dB, so it is negative 20 dB for omega bigger than 20. So from here we know that omega S is 20. Okay, so again, I want to remind you that you need to change the value of alpha, the value of alpha P or S, alpha S must be in decibel. And also, omega, when you want to use omega, it has to be in radians per second. Okay, you have to change, if the question gives you frequency, then you have to change to omega. Okay, so use this equation. Put in the value of omega S, alpha S and alpha P. And if you look at the equation here, this is divided by omega Sn. Okay, so you need to, I didn't put the omega Sn equation here. However, you can find it from your list of formula. for omega Sn. For low pass filter, omega Sn is given as omega S divided by omega P. So we put in the value of alpha S, alpha P, omega S, and omega P, and we find out that n is equal to 3.701. So this is very important for you to know. The calculated order n must be rounded to the larger integer number. So in this case, we round to 4. Okay, so it doesn't matter what is the value of n that you calculated. For example, let's say if you calculated n is equal to 3.2. So now you should not round this number to 3. Okay, you should round this number to the larger integer number. So n will be 4. Okay, so don't round it to 3 or don't round it to 3.5. No. Okay, should be integer and should be larger than 3.2, which is 4. Okay, and then we determine the cut-off frequency. Okay, for cut-off frequency omega C means that we put the value of n and use both omega C equations. Remember that we have two omega C equations. Okay, if we refer back to here, we have two omega C equations. We have the one using omega P and alpha P, and second one is using omega S and alpha S. Okay, so we put in the value. Okay, we will get this and this. Okay, omega C. This is in terms of radian per second. Choose omega C that fulfill the specification of either alpha P or alpha S. If both values fulfill specification, choose one. Okay, so in this case, you have to test the omega C that you obtain here, 10.693 and also 11.261 in this equation of alpha P and alpha S. Okay, so you put in the value of omega P, omega C, and omega S, and also omega C here to find alpha P and alpha S, and find out whether this alpha P and alpha S is between or fulfill passband gain given here and also stop band gain here. Okay, so you check. Okay, if is fulfill the specification of either alpha in and alpha S, you can choose that omega C. Okay, if you both values here fulfill all the specification of alpha P and alpha S, you choose only one. So in this case, omega C is equal to 10.693 is chosen. Okay, and then this is the most easiest part. Okay, because you have determined n. Okay, and now is equal to 4. You have also found out the omega C, which is the cutoff frequency. So now from the table F6A, okay, the table has the number, so you just refer to table F6A. You go to the n equal to 4. Okay, so you take out the value of A1, A2, and A3. Okay, so now A0 here is equal to 1, A1 here is equal to 2.6131, A2 is 3.4142, and A3 here is 2.6131. Okay, so now you refer back to the normalized transfer function here. Okay, it is given as 1 divided by these equations. Okay, so A0 here is by default is 1. Okay, so you just put the value. So remember, A1 is at the most right of the equation. Okay, so you shouldn't put A1 here. A1 is here. Okay, so you put the value of A1 here, and because this is n power of 4, so we should get up until A3. Okay, and the numerator is always 1 for Butterworth filter. So you just put the value 1 divided by s power of 4, because this is n equal to 4. Okay, for order. And then this is A3, this is A2, and also this is A1, and this is A0, which is 1. Okay, so now we already obtained normalized transfer function. Okay, so in order to find the real transfer function from the normalized, we have to use the frequency transformation. Again, this is in table F5. So for the low pass filter, S here we change to or replace to S divided by omega C. So for every S that exists in the normalized transfer function, we change it to S divided by 10.693. Okay, 10.693. So we divide here. Okay, and you calculate. So we can get. Okay, so normally I will accept your answer if you just leave it like this. Okay, because I know that you have already chosen the omega C, and it's actually troublesome for you to calculate because it involves lots of numbers. Okay, you can just leave it like this. Okay, so I can accept that answer. So again, this um, chapter is very easy if you know or if you extract the information correctly. Okay, this is the transformation of frequency filter. Okay, from here. Okay, for frequency transmission here. For low pass filter, we use S divided by omega C. Okay, in order to convert from normalized transfer function to real transfer function. Okay, the one in the bracket is for Butterworth. Okay, outside the bracket here is for Chebyshev. Okay, so we have low pass filter, high pass filter, band pass filter, and also band stop filter. One exercise for you. So I hope you try to do it yourself first, and then you can message me to ask for the answer. Okay, because this is very easy. What you have to do is just mathematics. Okay, you just need to put the value of this low pass filter with specifications inside the equations, and you can determine the value of order and also the normalized transfer function and also real transfer function. Okay, we will do some more exercises in class on how to obtain the Butterworth filter function. Okay, so with that, I thank you very much.